Precast solutions to stormwater and wastewater management. Man has been trying to manage stormwater and wastewater for thousands of years. Evidence of activity concerned with human health and water supply has been found in civilizations throughout human history. Sites excavated in the Indus Valley and in Punjab show that bathrooms and drains were common in Indian cities 4,000 years ago. Streets were drained by covered sewers 2 feet deep and made of molded bricks, cemented with a mortar of mud. Within the houses, drain pipes were made of pottery embedded in gypsum. Even 2000 BC, the Greeks and Egyptians had adequate supplies of drinking water for their cities, drained streets, had bathrooms in their houses, and in Crete, water flushing arrangements for toilets. The Incas also had impressive sewer systems and baths. As sanitary engineers, the Romans set a great example and left their mark in history. A public water supply was considered a basic essential of civic life. They had well-developed water supply systems and drainage systems, and their standards of engineering sanitation were not matched again in Europe and in North America until the 19th century. Studies show that Rome's water supplies exceeded 40 gallons per head per day and was supplied to public baths, fountains, and other public structures as well as private houses. At their peak, they were able to provide an estimated 300 gallons per head per day. Their aqueducts and cisterns can be seen all over Europe and were frequently copied in medieval times. The Cloaca Maxima is one of the world's earliest sewage systems. Constructed in ancient Rome in order to drain local marshes and remove the waste of one of the world's most populous cities, it carried an effluent to the river Tiber, which ran beside the city. The name literally means greatest sewer. According to tradition, it may have been initially constructed around 600 BC under the orders of the King of Rome.
The city's first major engineering achievement was the Cloaca Maxima, an extensive sewer system which still functions today 2,500 years after it was constructed. The Cloaca Maxima flushed runoff from Rome's city streets into the Tiber River. Engineers also used the sewer's underground pipeline to drain the marshland between Rome's hilltop villages. There they built the Forum, ancient Rome's downtown district.
The construction of the Cloaca Maxima is the key event in transforming Rome from a series of tribes living on disparate hills around a swampy marsh into kind of centralized, unified culture. The new Roman Forum that resulted from the draining of the Cloaca Maxima really allowed that culture to consolidate in one central place.
The Cloaca Maxima was but one example of early civilization's construction of storm sewer systems. Sewer pipe has been found in the ruins of ancient Babylon, which is now in Iraq, estimated to be built back in 3000 BC. Stone drainage channels built in 4000 BC can still be found on the Isle of Crete. Sewer manholes built in 3000 BC have been found in mainland Orkney, Scotland. As citizens in ancient Rome did back in 600 BC, people today also depend on the functionality and reliability of storm and sanitary sewer systems. There are about 1.2 million miles of sewer pipe in the United States alone. Systems in place are sight unseen, and people seldom think about them when they're functioning properly. However, if a system breaks down, it can certainly raise awareness on how important this infrastructure can be to daily life. Issues can occur when sanitary or storm sewer systems are improperly designed to accommodate the demand. Also, problems may arise when sewer components are poorly manufactured or installed. Many portions of our sewer infrastructure are failing due to aging. All these factors can eventually contribute to a variety of unfavorable situations, including leakage. When a sewer system, which is intended to be watertight, starts to leak, there can be serious ramifications to the surrounding environment, public health, and structural stability of the structures. When a sewer is leaking, sometimes it can undermine the surrounding soil by drawing in dirt into the sewer line, creating large voids. Loads above these voids can cause the ground or roadway to cave in. A mild example of these cave-ins are depressions that can sometimes be found around curb inlets, as seen here. This could also be due to improper compaction. However, undermining due to leaking at the joint between the pipe and structure can also be the culprit. Here is an example of a slightly more severe cave-in. We see workmen at the top of the hole caused by a sewer break in Seattle, Washington on November the 11th, 1957. The Ravenna trunk sewer line had been built in 1909. The original contractor on the project gave up because of the quicksand prevalent in the area, and it was this quicksand that contributed to the underground cave-in. A 330-foot deep sinkhole formed in February 2007 in Guatemala City and swallowed about a dozen homes, forcing the evacuation of nearly 1,000 people in a crowded neighborhood. Officials blame the sinkhole on recent rains and an underground sewage flow from a ruptured main. A spokesman for the Municipal Water Authority said the sewage main ruptured after becoming clogged. He said the city was aware of the blockage, and the Army had been considering a controlled explosion to clear the pipe, which carries both rainwater and sewage for much of the capital. The sewer ruptured, and massive undermining took place. When systems are overwhelmed by increased volumes that surpass their capacity, large pressures build up, which can lead to serious damages. Water will always find a way out. In some cases, the pressure causes the water to surge through the manhole casting. Here we see an extreme example of this phenomenon. This is a highway camera footage of a portion of I-35 in Minnesota back in July 1999. The stormwater system was severely overwhelmed by the storm event. The point is, to avoid having everything from dips in the road to Old Faithful in the middle of the highway, stormwater and sanitary collection and conveyance systems must be designed, manufactured, installed, and maintained properly. Now, let's look at sewer system components. The basic components of a sewer system can be divided into pipes and structures. The pipe can be round, elliptical, arch, or rectangular box culvert. Structures can include inlets, catch basins, and manholes. These basic components are assembled to form a system that collects stormwater and wastewater from homes, commercial properties and surrounding streets, parking lots and landscape out to the main sewer line, and conveys it from point A to point B by gravity or pumps for treatment and disposal. At times, conditions may require advanced stormwater systems. Large paved areas such as store parking lots can generate so much surface runoff that systems must be installed that can not only provide treatment, but also temporary storage to avoid overwhelming the main sewer lines. Structures that can provide a level of treatment can range from basic to complex. Drain inserts are manufactured filtration products placed in a drop inlet or a catch basin inlet to remove sediment and debris. A multitude of inserts exist in various shapes and configurations. Typically, the insert consists of a frame that acts as the support structure for the filtering media and sediment debris collection device. This frame generally rests beneath the grate of a drop inlet or is attached to the wall of a curb opening style catch basin. Typically, a collection device made of polypropylene, filter fabric, or stainless steel will be attached to the frame, fitting entirely within the dimensions of the inlet structure without blocking the outlet piping. Filtration media will be secured within the collection device and will vary by manufacturer. Media types include polypropylene, porous polymer, treated cellulose, and activated carbon, depending upon the targeted pollutants. A typical sand filter system consists of 2 or 3 chambers or basins. The first is the sedimentation chamber, which removes floatables and heavy sediments. The second is the filtration chamber, which removes additional pollutants by filtering the runoff through a sand bed. The third is the discharge chamber. The treated filtrate normally is then discharged through an under-drain system, either to a storm drainage system or directly to surface waters. Sand filters take up little space and can be used on highly developed sites and sites with steep slopes. These devices are considered to have relatively high pollutant removal capabilities, especially for sediment and associated pollutants. Water quality units, also commonly called trapping catch basins, oil grit separators, or oil water separators, consists of 1 or more chambers that promote sedimentation of coarse materials and separation of free oil, as opposed to emulsified or dissolved oil from stormwater. Some WQUs also contain screens to help retain larger or floating debris. And many of the newer designs also include a coalescing unit that helps promote oil-water separation. A typical WQU, as shown in the schematic, consists of a sedimentation chamber, an oil separation chamber, and a discharge chamber. These devices are appropriate for capturing hydrocarbon spills and pre-treatment of stormwater runoff. WQUs typically capture only the first portion of runoff for treatment and are generally used for pre-treatment before discharging to other best management practices. Hydrodynamic separators are flow-through structures with a settling or separation unit to remove sediments and other pollutants that are widely used in stormwater treatment. No outside power source is required because the energy of the flowing water allows the sediments to efficiently separate. Depending on the type of unit, this separation may be by means of swirl action or indirect filtration. Underground stormwater retention-detention systems capture and store runoff in large pipes or subsurface structures. Stormwater may enter the system through a riser pipe connected to a catch basin or other stormwater collection structure, and then it flows into a series of underground chambers or compartments for storage. This captured runoff typically is retained throughout the storm event and then released directly into the surface waters through an outlet pipe. This outlet is sized to release the stored runoff at predetermined flow rates that serve to reduce the effects of pollutants leaving a site during peak flows. These systems typically are constructed in newly developed areas where land cost and availability are major concerns. They will generally be located under parking lots or other paved surfaces in commercial, industrial, or residential areas. Combined sewer overflows, otherwise known as CSOs, and sanitary sewer overflows affect the quality of water resources in many parts of the United States. Over 800 communities have combined sewer systems, serving about 40 million people, mostly in the Northeast, the Great Lakes region, and the Pacific Northwest. CSO discharges during heavy storms can cause serious water pollution. A 2004 EPA report to Congress estimated that there are 9,348 CSO outflows in the U.S., discharging about 850 billion gallons of untreated wastewater and stormwater to the environment. EPA estimates that between 23,000 and 75,000 sanitary sewer overflows occur each year, resulting in releases of between 3 and 10 billion gallons of untreated wastewater. Portland is a city located in the northwestern United States, near the confluence of the Willamette and Columbia Rivers in the state of Oregon. Portland is Oregon's most populous city and the third most populous city in the Pacific Northwest. Approximately 2.2 million people live in the Portland metropolitan area.
River health is a prime concern to our citizens. but also, the beauty of the river, the ecosystems, and community health, which is tied to river health. Ideas were brought forward to update the sewer system to greatly reduce or eliminate combined sewer overflow into the Willamette River. But if you went back 20 years, the idea of swimming in the Willamette River would have been of concern. But you see more boating, canoeing, kayaking, fishing, which I think is evidence of cleanup efforts that the city has undertaken, creating a healthier riverway.
During heavy rains, a large portion of the runoff goes to the Willamette River. A portion of the runoff flows into the Columbia Slough. In the past, during rain events, combined sewers were overwhelmed to a point where the excess wastewater would be discharged into the Willamette River. The wastewater carried raw sewage that polluted this major waterway and negatively impacted the quality of life for Portland residents. Portland started the CSO control program in 1991 with a set of cornerstone projects that removed stormwater from combined sewers. Projects included disconnecting downspouts from sewer systems, using pervious pavers, installing street sumps and sedimentation manholes. Controlling the CSOs was key to improving Willamette River water quality. So in 1991, the state of Oregon gave the Portland Bureau of Environmental Services a final order to clean up the Willamette River and the Columbia Slough by December 1st, 2011. After nearly 20 years, the program is complete and added up to approximately $1.4 billion in costs. CSO solutions include projects to remove stormwater runoff from sewers and building new facilities to carry sewage and stormwater to the Columbia Boulevard wastewater treatment plant. With the installation of large pipe along the riverbank, a diversion is created for the overflow. The purpose of this diversion is to transport the combined sewer overflows that would normally flow into the river to a pump station and then eventually a treatment facility.
Well, the CSO program started around 15 to 20 years ago, and its purpose was to separate the combined sewer overflow system that was currently in place. And so there were two massive tunnels built under the Willamette River to contain the overrun during a storm event and hold it there until the treatment facility could handle treating it. So it sits under the river and then eventually is pumped into the treatment facility and treated.
Looking at the map of Portland, we see the east and west side big pipe on either side of the Willamette River. The pipes enter into the Swan Island pump station on the east side of the Willamette, which then directs the water through the Portsmouth force main north to the Columbia Boulevard wastewater treatment plant. The Columbia Slough consolidation conduit also flows directly into this treatment plant. Construction of the Swan Island pump station and the west side big pipe was completed in 2006. The west side big pipe measures 14 foot in diameter and is 3.5 miles long. The east side big pipe measures 22 foot in diameter and is 6 miles long. As a result of this project, CSOs to the Willamette River have been reduced by 94%. Some of the pipe was installed using a micro-tunneling process. That method is similar to ones used for massive underground projects, such as the Big Dig in Boston and the Channel underneath the English Channel. This process allows the pipe to be installed without interrupting commerce or disturbing utility services buried under the surface of streets and roadways.
Well, the micro tunnel process is you've got your tunnel boring machine, which sits was the first thing they launch into the hole. The tunnel boring machine has a cutting head. It's 50 feet long overall, 10 foot long segments. It's quite a machine, but it has no method of self-propulsion. So the only way to get the machine to move forward is to put a piece of pipe behind it and then push it with a couple hydraulic rams. So what they do is they push the machine into the hole first, then they'll load in their first pipe. They will push the pipe with the rams, retract the rams, load in another pipe, push, and so on. Now, every time they put in a new piece of pipe, there's conduits, there's plumbing, there's air ducts, all sorts of things need to be connected and plumbed inside that pipe before they can start pushing.
At the launching station, a section of pipe is lowered into position. Hydraulic jacks then push the pipe forward, which propels the drill head through the earth until it emerges at the reception station. The drill head is not self-propelled. It moves forward due to the pressure exerted via the hydraulic jacks in the launch tunnel. The hydraulic jacks produce a substantial axial load on the pipes, which serve as a conduit for the jacking forces to propel the drill head.
So it's very critical that each pipe in the string, performs. Because if one were to fail, if one link in the chain fails, the machine is stuck. And that could be a real problem.
So, what do ancient Rome and present-day Portland have in common? Concrete. Just as we do today, ancient civilizations chose concrete as their material of choice. Many of the pipe and structures unearthed recently by archaeologists were made of concrete. Modern technology enables us to move the manufacturing of concrete from the variable conditions in the field to a plant environment which greatly enhances quality control. Concrete that is cast elsewhere than its final position is known as precast concrete. Precast concrete structures are manufactured in a controlled environment that enables careful monitoring and management of quality control procedures. Let's go through the typical manufacturing process. The production cycle begins with setting of the forms. The core for this section of large diameter precast pipe is set in place. Reinforcement for this section of pipe is assembled in another area. This cage machine precisely measures, cuts, and welds lengths of plain and deformed wire to form the reinforcement cage. Additional deformed rebar is placed and tied onto the cage according to design drawings. This will further enhance the pipe's ability to withstand stresses in the field. Manhole cages are built in a similar fashion, while inlet and box culvert cages are assembled by hand. After form release has been applied to the core, the steel reinforcing cage is put in place. The diameter of this cage is manufactured to exacting dimensions and has to be carefully placed to maximize its efficiency while providing enough concrete cover to protect it from the elements. In this case, design calls for an additional slightly larger diameter cage to be placed in the form as well. Engineers consider all loading conditions, including handling, shipping, installation, and service loads when performing these designs. Standoffs are placed to keep the cage in the right position so they don't shift when the concrete is poured. A quality control technician carefully looks at the cage prior to closing the form to ensure that proper clearances are in place. This is referred to as the pre-pour inspection and is one of many quality inspections performed throughout the manufacturing process. The form's outer jackets are coated with form release and then assembled. Other drainage structures such as manholes, inlets, and box culverts go through a similar pre-pour process. If a manhole or inlet is designed for pipe entrances, the QC technician will verify the positions of blockouts prior to closing the form. The batch plant operator then fires up the mixer. Most batch plants are automated and measure and dispense specific amounts of raw materials according to the designated mix design. Once the batch is mixed, it is dumped into a bucket, which transports the fresh concrete to the form. The concrete is carefully deposited to avoid segregation and is consolidated into place with the use of vibratory equipment. Consolidation is a critical step in the process as it is used to drive out entrapped air, which, if not removed, may increase porosity and therefore lower the strength of the concrete. During this time, testing of the fresh concrete is performed. Here we see a spread test. Spread tests are done when using self-consolidating concrete, also known as SCC. Once the cone is lifted, the technician measures the spread, which is an indication of proper water-cementitious ratio. Conventional concrete has a similar test, called a slump test. Other tests include temperature, unit weight, and air content. Cylinders of fresh concrete are placed in curing conditions similar to that of the product, so accurate measurements of the 3, 7, and 28-day strengths of the concrete can be taken. Some cylinders are placed in a water bath to provide 100% moisture for quality control laboratory testing. All of these cylinders will later be used to measure the compressive strength of the concrete. Once concrete products are poured, they are left in the forms to cure until they reach the required stripping strength. Different methods of curing are used depending on conditions and product type. Curing enclosures are sometimes used to help provide adequate moisture and temperature. Proper curing is essential in ensuring the cement fully hydrates, maximizing hardened concrete's characteristics. Once minimum stripping strength is achieved, the products are stripped from the forms. They are inspected by the quality control technician to ensure they meet specifications and design drawings. After the QC technician approves the product, it is marked and moved to the storage area. This post-pour inspection is a critical element of any precast plant's quality control program. Any product out of tolerance is marked accordingly and stored in a separate area or crushed and recycled. When it's time for delivery, products are loaded onto trucks and securely fastened to the bed. A QC technician will then perform a final inspection to ensure the proper products are being shipped and that no damage has occurred during handling. The precast concrete products are then delivered to the job site for quick and easy installation. When choosing a material for sewer structures, several factors should be considered: quality, strength, water tightness, durability, buoyancy resistance, ease of installation, and sustainability. Let's start with quality. The quality of precast concrete products depends on the quality of the raw materials, including aggregates, cementitious materials, water, admixtures, and reinforcement. Aggregates are an essential ingredient in concrete. They can consist of 60 to 75% of the total volume of concrete. For a quality concrete mix, aggregates need to be clean, hard, strong particles, free of absorbed chemicals or coatings of clay and other fine materials that could cause the deterioration of concrete. The correct gradation of aggregates is also crucial. Aggregates are divided into two distinct categories: fine and coarse. Quality and grading are controlled by very strict requirements, including those of ASTM C33, standard specification for concrete aggregates.
The aggregates that we get go through a process control. So our suppliers are providing us with process control that is state compliant. So there's a lot of testing that goes into it. Some of this will include ASR testing to see if that's applicable, if we've got something that's expansive, to sodium sulfate soundness testing. So our aggregate right from the get-go is being tested. It gives us a certain level of quality right from the beginning. So we know we've got a product that's had to pass quality tests and that is being tested on a consistent basis that meets the DOT standards.
Cement used in the manufacturing of precast concrete is known as Portland cement and is considered a hydraulic cement. This means it reacts with water, a process called hydration, to harden it as it cures. Portland cement used in precast concrete must also adhere to strict requirements, including those of ASTM C150, standard specification for Portland cement. Supplementary cementitious materials, or SCMs, play a key role in enhancing the quality of precast concrete. They contribute to the properties of hardened concrete through hydraulic or pozzolanic activity. These materials react chemically with calcium hydroxide released from the hydration of Portland cement to form cement compounds. These materials are often added to concrete to make concrete mixtures more economical, reduce permeability, increase strength, or influence other concrete properties. Typical examples of SCMs are natural pozzolans, such as fly ash, ground granulated blast furnace slag, and silica fume. Almost any natural water that is drinkable and has no pronounced taste or odor may be used as mixing water for precast concrete. However, some waters that are not fit for drinking may be suitable for concrete as long as it meets the requirements of ASTM C1602, standard specification for mixing water used in the production of hydraulic cement concrete. Chemical admixtures are the ingredients in concrete other than Portland cement, water, and aggregate that are added to the mix immediately before or during mixing. Producers use admixtures primarily to modify the properties of hardened concrete and to ensure the quality of concrete during mixing, transporting, placing, and curing. Examples of concrete chemical admixtures are air entraining, which is recommended to improve precast concrete's resistance to freezing when exposed to water and de-icing chemicals. Water-reducing admixtures, which will reduce the required water content for a concrete mixture and increase its strength. And accelerating admixtures, which will increase the rate of early strength development, reduce the time required for proper curing and protection, and speed up the start of finishing operations. Reinforcing steel is used in precast concrete to enhance its ability to counter forces in manufacturing, handling, and in service. Precast concrete is weak in tension compared to its compressive strength. Steel reinforcing is very strong in tension and will absorb tensile forces in the concrete to prevent failure. Selection and placement of reinforcement is crucial to enable it to do its job. Quality is governed by many requirements and specifications, including ASTM's A615 and A706. These raw materials are inspected and controlled by QC personnel. However, this is but one of many factors involved in a thorough quality control program.
It's pretty extensive. If you do it right, you have to, all the way down to the certification of the steel. You have to check the weights of the steel. You have to check, there's testing to make sure that the aggregate is correct, sieve tests and water tests. And then we test the probes in the mixer to make sure they're calibrated correctly and that the right water cement ratio is going into the pipe. And then we check the steel clearances on everything before we pour the concrete, the clearances between the form and the steel to make sure if you don't get any corrosion, water infiltration, it's not going to reach the steel. And then after the finished product is out, then we check it again to make sure it's right again. And then before we ship it, we check it for squareness. Like if it's a lay down pipe, like such as these, we have to make sure that it's square. And these are being pushed through the ground. So we measure it 19 different ways to make sure it's square. We check all the wall thicknesses to make sure they're within spec. We check it to make sure there's no exposed steel. We make sure that the bell is correct, the protrusion is correct to support the rubber gasket going in. It's my name on that product. I'm the final person that looks at it. And that means a lot to me. And I'm not going to let something slide through that isn't right.
Precast concrete strength is defined by its ability to withstand stresses. It relies mostly on the quality of the aggregates and proper production and curing practices. Precast concrete strength is usually expressed in pounds force per square inch of resistance to compressive loading. The compressive strength of precast concrete is measured by breaking cylindrical concrete specimens in a compression testing machine as per the requirements of ASTM C39. The load is increased until failure, and that load is divided by the cross-sectional area of the specimen, resulting in the compressive strength of the concrete. Precast concrete pipe has to meet several acceptance requirements as per ASTM C76, standard specification for reinforced concrete culvert, storm drain, and sewer pipe. One of these requirements is the 3-edge bearing test. Expressed in pounds per linear foot per foot of inside diameter, this method tests the pipe under severe loading conditions where there is no bedding and no lateral support under 3-point loads. The standard for this test method is ASTM C497. A force is gradually applied over the length of the pipe until a crack having a width of 0.01 inches over a length of 1 foot appears. The load is measured and has to meet or exceed the specified load, referred to as D load in ASTM C76 for that class of pipe. The pipe is then crushed to failure, and that load is measured and has to meet or exceed the specified ultimate D load. In the case of the CSO project in Portland, Oregon, strength was a key factor in the selection of precast concrete pipe. Not only would this pipe be subjected to large stresses in service, but it would also be subjected to tremendous jacking loads during installation.
It's actually a well-designed pipe, and it's designed to take these jacking loads. We've got a jacking system that's capable of producing 900 tons onto that pipe, and it can take more way over that actual jacking load.
Horizontal or axial loads exist primarily during installation. Vertical loads on the pipe include the soil load above the pipe, the weight of the pipe, the weight of fluid within the pipe, and any live load or surcharge loads. Pipes are designed so that when subjected to external forces, reinforcing is placed in key areas to help the concrete withstand tensile forces. Forces on an inlet and pipe system include live loads from traffic, surcharge loads, and soil loads. These loads are all considered when engineers calculate design criteria, such as the size and placement of the reinforcing. Let's look at water tightness. Water tightness is defined as such tight construction or fit as to be impermeable to water, except when under sufficient pressure to produce structural discontinuity. The goal is to minimize porosity and permeability. Porosity is the ratio of the volume of openings to the total volume of material. In other words, porosity represents the storage capacity of the material. This is controlled by carefully monitoring and controlling the water cementitious ratio of the concrete mix. Just enough water is required to properly hydrate the cement. Excess water will evaporate and leave pores in the concrete, therefore increasing porosity. Permeability is a measure of the ease with which fluids will flow through a porous material. So the higher the porosity, the higher the permeability, and the lower the level of water tightness. Many systems, especially sanitary sewers, are required to be watertight. Precast concrete products manufactured in a quality-controlled environment and used with high-quality sealants and connectors offer a superior solution to water tightness requirements. Manufacturers of precast concrete pipe test water tightness by performing a vacuum test.
With a vacuum test, we're basically plugging either end of the pipe and we're putting it under a certain vacuum and we're seeing how long it takes for us to lose that vacuum. We're basically measuring the same thing. We're seeing if this is a tight product, if this is a product that is not going to leak.
Vacuum testing is a quick, safe, and practical way to validate manhole system integrity. Manhole sections can be tested at the precast concrete plant prior to delivery or on site prior to backfilling. Vacuum is defined as an absence of matter in a defined volume of space. To produce a vacuum in the field, we need to remove air from within the manhole structure. Initially, a manhole, which has not been backfilled, is uniformly loaded by atmospheric pressure of 15 pounds per square inch atmosphere on its interior and exterior, creating an equilibrium state. To create a vacuum, we use a pump, or Venturi nozzle, attached to the manhole and attempt to suck out the air to create a pressure differential between the partial vacuum inside the manhole and the atmospheric pressure pressing against the exterior of the manhole. When a vacuum of 10 inches of mercury is drawn on a manhole, an internal pressure of roughly 10 pounds per square inch atmosphere is created. The atmospheric pressure on the exterior of the manhole, 15 psia, will thus exert 5 psi differential pressure on all surfaces, joints, and connectors. No other test method uniformly tests a structure in this way. ASTM C1244, standard test method for concrete sewer manholes by the negative air pressure vacuum test prior to backfill, has been developed to govern the proper vacuum testing procedure for testing concrete manholes. Let's briefly look at a manhole and pipe system to learn about materials used to ensure water tightness. Starting at the top, the casting usually sits on risers for grade adjustment. Watertight castings can be installed and joint sealant is used between the risers. Interior seals can also be used to provide additional protection from water infiltration. Moving down to the first joint between the cone section and the riser section, we see examples of different joint configurations. Gaskets can be used at the joints, which will provide a watertight seal when the joints close. Flexible sealant can also be used to provide additional protection against water intrusion. Exterior joint wrap can also be used in certain conditions that may require additional watertight protection. Finally, let's look at the base section where the pipes enter the structure. Pipe connections to the manhole are sometimes grouted in the field, but this may not provide a watertight seal. In order to ensure water infiltration and exfiltration are avoided, it's best to use flexible connectors, such as a boot type or compression type connector. These will move with the pipe, maintaining a watertight seal. Joint sealants, gaskets, and pipe connectors are all manufactured to strict quality control requirements and are tested to meet ASTM specifications. Only these products can be used in approved precast concrete drainage structures. Let's look at durability. Durability of precast concrete may be defined as the ability of concrete to resist weathering action, chemical attack, and abrasion while maintaining its desired engineering properties. Different concretes require different degrees of durability, depending on the exposure environment and properties desired. For example, precast concrete exposed to tidal seawater will have different requirements than an indoor precast slab. Concrete ingredients, their proportioning, interactions between them, placing and curing practices, and the service environment determine the ultimate durability and life of concrete. Now let's look at buoyancy. Buoyancy is defined as the tendency of a fluid to exert a supporting upward force on a body placed in a fluid. It can be determined if an underground concrete structure will float or sink using basic principles. Essentially, a structure will not float if the sum of the vertical downward forces is greater than the vertical upward force. Precast concrete structures have an advantage over other materials due to its high specific gravity of 2.4, which allows it to resist buoyant forces. It will not collapse or float out of the ground in high water table conditions. Let's look at ease of installation. Precast concrete structures are engineered materials and do not rely mainly on engineered installation as other materials do. This means the structure is designed to counter forces on its own, despite the nature of its underground environment. Also, it comes to the site ready to be installed, reducing the need for large staging areas. Weather dependency is also not an issue when installing precast concrete products. This is why contractors love to work with precast concrete.
The precast, compared to the old ways or any other way that I would know how to do it, is really cut the manpower down probably, I say 40%. It sounds like a lot, but it is, because the one crew that does the pipe does the manholes. So that's just a bigger, flatter piece of pipe in our eyes now, is the way we look at it.
Let's look at sustainability. The use of precast concrete structures is a sensible choice for sustainable development. Precast plants reuse formwork, in itself a conservationist move, and in doing so, reduce construction waste that would otherwise be generated at a job site. Because precast concrete components are modular and standardized, they are installed in a quicker fashion and result in reduced construction times and energy usage, noise and emissions from on-site equipment, and in reduced site impact. The cement used in concrete is made of natural materials such as limestone and clay. Most cement plants rely on nearby limestone quarries.